Sushruta for NEET is now available on the Google Play Store. Try it out for free.
Today, we continue our discussion of thermodynamics. Okay, so today we'll try to wrap up thermodynamics, and then we will move on to next the next set of ideas, which is kinetic theory of gases. We should have probably done kinetic theory of gases earlier, but I prefer to this time do it in this order so that you kind of understand the macro before you look at the micro. Okay, so kinetic theory of gases uh, also see thermodynamics is a is taught from a macro perspective, right? We talk about engines, we talk about systems, right? It's a system science. Okay, while kinetic theory of gases then links the ideas to the micro understanding of things. Okay, the micro and the macro are all related, you know, and it's true in physics, it's true in economics. Okay, so what we teach in through our platforms and through our apps, right, are integral part of the education you get from our system. Our system includes these lectures as well as what you get from our apps. Okay, these lectures, the Jnanamarga study methodology uses the is a best of breed that allows students to both read the textbook, view the slides, watch the videos from one integrated viewpoint. Okay, that is the main advantage, and we use the IIT PAL lectures to in addition to our own lectures. Okay, so our NEET is available in two versions. One is our tablet version, and the other is the our device, cell phone version. Okay. Now, each of these is an Android application. So you download the application, you then try to register, and then you have 2 free weeks, and then you have to look to buy it, or you can buy it through your school. Many schools today also offer Sushruta for NEET, and also the CBSE 12 app, which is also affiliated to this. Attending these lectures is free. Okay, they happen every weekend, and we have maths, physics, chemistry, and biology. Okay, so having said that, let's get going. Okay, so we are towards the end of the year, and this is probably one of the last weeks that we will use to complete our the final parts. There is a little more that we have with class 12, but the class 11 is going to very soon end, and we are going to be starting a new year. When we start the new year, right, we will start first with a little calculus, then we will build on top of that. Okay, but today, the integrated learning platform, let me explain how it works. Okay, a student for physics in particular, if he buys the tablet, gets HC Verma as an ebook. You can, of course, if you have your own cell phone, you can also download Kindle and then get HC Verma on Kindle. Okay, then if you are a NEET student, you get on top of that biology and chemistry. Okay, so then you have your three books: physics, chemistry, biology. Then you have A to Z. Okay, now we typically the A to C books are on paper. This is for the students who buy our tablet system, and that is a little more expensive. Okay, so typically speaking, the student should purchase, in addition to based on their, if they are taking NEET or they are taking JEE, they should buy these additional books right up front. They can either buy them through their own through their own resources. Otherwise, they can use our tablet based purchase platform. Okay, so now available for free download is also Ramanujan is our JE app. Okay, and it is very very similar. Again, you get HC Verma for maths. we recommend Tivani, okay, particularly for students preparing for the JE mains. And you also get the last 40 years question bank from one of the sellers. We typically work with CNGage, or we work with one or two other providers. Now the NCR, the NCRT books come with our apps, and then you get your slides and IIT PAL videos. Now, if you buy the integrated platform, you also get e-abhyas, etc. Now, you also get our Jnana chat. Jnana chat is very, very helpful for students because you can then ask some questions and get them answered either by other students or by our tutors. Okay, so this is the breakup of the JE mains, right? So you have the neat breakup is also here. I'm not sure if you can see this slide. Okay, let me try and right. So here you see right now we are doing thermodynamics about 9% of the paper, right? Alternating current, right? Atoms, right? Electromagnetic induction, etc., right? So work, power, energy, right? And you have laws of motion. So there is corresponding weightage, right? In neat physics you have 45 questions. So how many questions can they ask? Two questions, three questions? If they ask two questions, that is a significant portion of the weightage. Okay, if they ask three questions, then you really have to prepare yourself for the material, right? Now neat, because it's a very time limited exam, tends to be much more conceptual, while JE, on the other hand, is they expect you to be able to do calculations, and there are fewer questions there, because they want you to spend more time and be able to solve questions. Okay. Now, today we are going to continue with our understanding of heat engines. Now, a heat engine is a machine that turns the energy locked in fuel into work. Okay? It takes, like, all of you know what coal is. It is old rocky stuff, and today of course there are also engines which use diesel, right? So you burn it in an engine and then you can release energy, right? It is used to power the energy to power machines, and all these, like, diesel, etc., are used to power cars, boats, or locomotives. Now natural gas, wood, and peat, right? All these are used as fuel, right? So since engines work by burning fuel to release heat, they are sometimes called heat engines. It is a common name, and it is a name that originates in this subject we are studying, thermodynamics. Okay. Now when you burn a fuel, it undergoes a chemical reaction called combustion, and when you that chemical reaction, when the fuel burns in oxygen, produces carbon dioxide, and typically it is used to and steam. Okay. Now engines also of course create air pollution. There is some amount of coal particles that get emitted, etc., right? So there's a lot of pollution from all this. Now and but then the process of making um, of doing work, right, involves the transfer of heat. So think of this as the engine, right? So there is a certain amount of heat supplied to the engine. Okay. Now that heat, okay, so that heat is then uh, there are two things that happen. Some of that heat is converted to work, and some of it is then passed on to a system or a control volume. Okay. Now you got to think of the air conditioner also has a heat engine. Okay, only thing it's a heat pump. Okay, a heat pump is the inverse of a heat engine. We will look at heat pump later. Okay, now in a heat engine, heat is transferred and work is done. Look, think of the steam engine, right? Choo choo train, right? You would have all heard of this choo choo train, right? Near my house, there is a school called Choo Choo Train School, okay, for little children. Now, in when you look at what happens here, right? Some of it goes into work, and some of it is just garnered as internal energy of the system, then evaporates. Now, in many thermal reactors, they are also heat engines. What is a thermal power station, right? Thermal power station, what does it do? They burn coal or natural gas, and then they convert that to mechanical and then electrical energy. Okay? So the aim there is to use electromagnetic induction, which we are doing now in class 12, right? Use electromagnetic induction to generate power. Okay, but it is also finally a heat engine. Now, a portion of the heat, right? Not all the heat can be converted to work. That is second law of thermodynamics, Kelvin statement. We already looked at this, right? Kelvin statement, right? Then Clausius's statement, right? Not all the heat supplied can be converted to work, right? So what portion is converted to work decides the efficiency. So some of it is passed also as heat. So Q1 minus Q2 by Q1, right? Q1 is the heat supplied, right? Q1 minus Q2 is what is the work. So W by Q1, right? So you have the so you will never get an efficiency of 1. There will always be a Q2. Q2 will never equal 1. So that is what Kelvin and Clausius said. Now, a refrigerator is a machine for keeping things cold. So how does a refrigerator work? You use electricity. It is called a heat pump. Okay, it takes heat from a place which is already very cold. By doing work, it takes heat from a place which is already very cold, and then transfers it to a place which is warmer, right? Normally, as you all know, heat is lost as per Newton's law of cooling, right? Heat is lost by something that's hot and gained by something that's cold. A heat pump, on the other hand, reverses that process by doing external work. So how does it do? It takes this liquid called freon, and then which is liquefied under pressure. So that is where you do the work. You liquefy it, then it passes through a this freon, right? It passes through it is coiled around your fridge, right? And then it absorbs the heat of the substances inside the fridge, right? So it absorbs the heat, and then the fridge is kept completely closed. The freon is in a system, right? Is this uh, uh, adiabatic? No. Is it isothermal? No. It is absorbing the heat, right? And so what happens there? Absorbs the heat, and then it passes it to it gets converted back to vapor, right? It's converted back to vapor, and then that vapor is then recompressed. So there's work again done. So in this case, this is the heat pump. This was the heat engine. There is work done by the system, right? Here there is work done on the system to compress, and therefore it takes heat from a place of cold and then passes it to a warmer place. Here, T1, which is the outside ambient area, right, is actually at a higher temperature. T2 is at a lower temperature. Here, T1 is at a higher temperature, right? Because it's the hot, the burning coal, right? Then the gas is converted and then it's passed on, right? A heat engine like is most often, very typically a control volume. That's why you have so many people talking about greenhouse gases. Okay. So here too, you can define a efficiency. Okay. So here, how much of the work gets converted to, if all the work was to be completely converted to the uh, transfer of the temperature, to reducing the temperature, right? All the work was to be converted to pushing the heat. Okay. So here Q1 equals, Q1 is the is the heat that is transferred out, right? Equals Q2 plus W, right? You have to understand that here again, you cannot make the COP be infinity. When will it be infinity? If you can do no work, and you can take energy from heat from one place and pass it on to another. W has to be non-zero. Okay. Here Q2 over W, right? Q2 is the temperature that is the heat that is drawn from inside the fridge, right? Q2 is the heat that is drawn from inside the fridge, and given T1 is the ambience. Okay, T1 is the temperature of the ambience, right? T2 is less than T1, keeping it colder than the ambient temperature, right? So Q2, right, is the heat taken out, right, from the fridge. W is the work done on the system, which is the freon gas, right? And Q1 is the heat that is added to the ambience. Okay, if you didn't have to do any work, if you just could make these, infinitely efficient machines, then you will have to do no work, right? But you do have to do work. That is the second law. So Q2 by Q1 minus Q2 will give you the corresponding efficiency. Q2 will always be less than the work done. Okay. So perpetual motion cannot happen, right? Work without the input of energy cannot happen, right? We already know that perpetual motion machine cannot happen, right? Then you have perpetual motion machine of the second kind, which is the second law of thermodynamics. So now we've defined the efficiency of these machines, right? No cyclic process whose sole result is the absorption of heat from a reservoir and the complete conversion of the heat to work. Okay, so that is the one version of the second law, right? No cyclic pulse whose sole ability is to transfer heat from a colder body to a hotter body without any. That is the Clausius statement. This is the heat pump statement. This is the heat engine statement. Okay, so Clausius statement is applies to the heat pump. Kevin Planck applies to the heat engine. One is the engine and the other is the pump. Okay, but both actually state the same law. They're actually, so there is now, what they are effectively saying is that the there is in any, there cannot be really a reversible engine which takes everything from and comes back to the same state, and while there is work done and there is also heat transfer. Okay, so so that is the fundamental idea in the second law of thermodynamics, and this Carnot engine is a way to understand it. Okay, so Carnot further explained what's going on, and so he was the first to give this theory of maximum efficiency, define the maximum efficiency of these heat engines. Okay, and he used this comparison between the PV and the TS, and then he explained it very well. And that successful theory was then reapplied by many in who then um, Kelvin and Clausius, right? We just now looked at the Kelvin statement, which is the heat engine version, and the Clausius statement, which is the heat pump version. Okay, so you have four parts. There are four processes: one, two, three, four, right? You remember P versus V, T versus S, right? So P versus V, right? Isothermal. Isothermal is what? And then adiabatic, right? Isothermal, adiabatic. Isothermal, adiabatic. Okay. So what is isothermal? Constant temperature. Okay. So at a constant temperature, there is heat transfer. Isothermal means PV is a constant. Okay. Adiabatic means PV to the power of gamma is a constant. Adiabatic means there is no heat transfer. Okay. So isothermal means there is heat transfer, but the temperature is constant. Adiabatic means there is no heat transfer, but PV to the power of gamma is a constant. Okay. So here there is isothermal, PV is a constant. Adiabatic, both are expansions. Why? When we say expansion, what do we mean? The volume increases. Isothermal expansion, adiabatic expansion. Isothermal compression, adiabatic compression. And then you come back to the same original state of P versus V. But along the way, this is what? PDV is the work done. Integral PDV is the work done. The area inside this parallelogramic, this is not a parallelogram. PV is a constant, is a parabola. PV to the power of gamma is a constant, is a different type of, is not a parabola, hyperbola. This is a hyperbola. PV is a constant, is a hyperbola. This is a different type of hyperbolic curve. Okay. So this is a hyperbola, but it is, the movement is from this way to that. It's a compression. This is also a adiabatic compression. Isothermal, adiabatic. Isothermal, adiabatic. That's how the Carnot engine operates. So you have a, uh, uh, pa- uh, hyperbola based parallelogram, which brings you back to the original point. PV is a constant, PV to the power of gamma is a constant, PV is a constant, PV to the power of gamma is a constant. This is the Carnot engine. Okay, and in a Carnot engine, work done in the closed loop is the area inside the curve. PdV, integral PdV is the area. Okay, so integral PdV will give you the whole area. Now, when you have these back things, they remove the area underneath. So that's the negative work, right? So here there is positive work, here there is negative work, but there is a net amount of work, which is the area inside the curve. Okay, so now isothermal adiabatic, right? Isothermal adiabatic. Now, what does that do to the T versus S curve? Integral TdS is what? Integral PDV is the work. Integral TdS is the heat. Okay. So this one, isothermal has heat, right? Has heat transfer into the system, right? Adiabatic has no heat transfer because S is constant. In adiabatic, what is constant? S is constant. Therefore, there is no heat transfer in adiabatic. Okay. So now here there is every one of the processes has work done. Okay. But here, this and this, there is no heat transfer. Okay. So there is heat supplied and heat removed. Okay. Heat supplied is positive, heat removed is negative. Okay. So the area inside this box rectangular box, the area is the net heat supplied. Okay, so what is the efficiency of this Carnot engine? It is the work by the net heat. So W by Q will give you the net efficiency. Okay, that is the net efficiency. Net work by net heat. So the first case, PV equals nRT. Step 1, PV equals nRT. So RT ln V2 by V1. Second case, you have PV to the power of gamma as a constant. So the work is R times T1 minus T2 by gamma minus 1. This is just PV to the power of gamma as a constant. So you do that integral. PdV, you do that integral, you will end up with this formula. Then, but then here, there is no heat transfer. Okay, so here there is work done, and then there is also heat transfer. Okay, so now the net effect is that some of the heat has to be supplied to produce a increase in the internal energy. Okay, so Q1 minus Q2 will be the work done. So the efficiency is Q1 minus Q2 by Q1, right? And therefore you can evaluate from that the net efficiency of the Carnot engine. Okay, so so using these formulas, you can then evaluate the net uh, work done. Okay, so Q1 minus Q2 by Q1 is 1 minus T2 by T1 ln V3 by V4 by ln V2 by V1. Okay, from these two, you can then look at the there is no cyclic process possible, where the sole result is the absorption of heat from the reservoir, the complete conversion of the heat to work. Given two heat reservoirs, a Carnot engine has the maximum efficiency of all reversible engines working between two given reservoirs is the same. Okay, so regardless of the working substance, the substance employed, or the operation details. Okay, so now what is the basic idea here, right? So the basic idea here is that the work done is Q1 minus Q2, and the efficiency is Q1 minus Q2 by Q1. Okay, so uh, the if you have a Carnot engine which is operating as a refrigerator and a reversible, both are being operated between a hot reservoir and a cold reservoir, right? You, in a Carnot engine, what you're trying to do is you're trying to transfer heat from an area of cold to an area of warmth, right? Cold reservoir is T2, that is inside the fridge, and warm reservoir is the ambient side, which is the T1. Similar to an AC, right? Now, so this is the basic idea, that the net effect, you cannot have all the heat transfer and no without any work being done. Okay, so that is the if there was such a possibility, it would then violate the second law of thermodynamics. Okay, so let's look at a few problems today. A sample of water is slowly heated from 27 to 87. Calculate the change in the entropy of the water. So change in the entropy is what? Delta Q equals ms delta T. So delta Q by T will give you the delta Q is ms, delta Q is also delta S by T, right? So when you divide the two, you have delta Q by T equals delta S. So ms delta T by T, right? So if you do ms delta T by T, so then you will end up with, you take the ms out, dt by T. Dt by T will give you what? Right? Delta Q by T will give you the delta S, right? So dq, and you integrate all those delta S's, you will end up with the So ms delta T by T, right? So ms delta T by T will give you the entropy, right? So the change in the entropy, right? The change in the entropy is ms delta T by T. So integral dt by T is ln T. So ln T2 by T1. So T2 by ln T2 is what? 87 degrees. 87 degrees is, so in Kelvin it is certain amount. What is and specific heat capacity is 4200, right? So correspondingly, you can calculate the 4200 times ln 87 by ln what is that? 273 plus 87 divided by 300. 273 plus 87 is what? 360. Ln 360 by 300 is ln of 6 by 5, right? Ln 6 by 5. Okay, so 4200 times ln 6 by 5, okay, per kg. So that's a very simple question to calculate the entropy. Okay, so uh, in a cyclic process, work done by the system, in a cyclic process, work done by a system is zero, equal to the heat given to the system, more than the heat given to the system, independent of the heat given to the system. In a cyclic process, work done by the system is zero. Well, not necessarily, right? If you had PdV, you can come back to the original place, but the work will not be zero, right? Now, equal to the heat given to the system, that can never be true because of second law of thermodynamics. More than the heat given to the system, also not true because of second law of thermodynamics, right? So independent of the heat given to the system. Well, that's not necessarily true. Okay, so this is a really tricky question for that reason. Okay, the uh, the real point here is that the work done in a heat pump, right, will be more than the heat taken out of the system. Okay, it will be more. So C is true, right? It so if if you look at the system as as the freon gas, right? The heat given to the freon gas, right? So that is the, if it was like that, then C would be true, right? But then uh, in a cyclic process, the work done by the system is not zero, right? So independent of the heat given to the system, right? So it is in some way actually related to the heat given to the system, but you would probably pick that because it is never going to be equal to the heat given to the system. According, zero is not true, PdV, right? Equal to heat uh, uh, given to the system, it will never be true, right? So more than the heat given to the system, not possible, right? So B and C are never true, right? Because of so the only possibility is D, right? So that's the only answer you can do. It's very tricky because it has a hidden assumption. Okay? Hidden assumption is that you are operating a heat engine. Okay, so and in a heat engine, you have to then apply the Newton's law. Okay, so not Newton's law. You have to apply the second law of thermodynamics. Okay, so Kelvin's. Okay, so a sample of an ideal gas has pressure P naught and V naught. So this is a PdV question. PV, P versus V, has V naught and P naught, V naught, and T naught. It is isothermally expanded to have twice the volume. Isothermally means what? PV equals constant. It is then compressed at constant pressure. Okay, find the, okay, now show the V versus T diagram and calculate the heat absorbed. So they don't want to see the PV diagram, right? They want to see the V versus T diagram. V versus T. So initially the V versus T, it is isothermally expansion. So V and T, right? So T is constant, isothermally expanded from A to B, right? It is then compressed at constant pressure to have the original volume. Okay, so the V, it comes back to constant V, and then finally the gas is heated at constant value to get the original. So A to B, then the it is then compressed at constant pressure to have the original volume. So what happens when you have constant pressure, right? When you have constant pressure, what happens to the V versus T? PV equals nRT. Ideal gas means PV equals nRT. So if the pressure is constant, your volume will decline with temperature. V versus T will be a straight line. PV equals nRT. P is constant. V equals KT. Okay, so it will be a compression, and the compression will be along a straight line. So BC, AB, isothermal expansion, V versus T, right? BC straight line, right? And then CA. Finally, the gas is heated at constant volume. V versus T, constant volume increases the temperature. Okay, so A to B, B to C, C to A. Okay, now calculate the heat absorbed. Okay, so if you have a V versus T diagram, right? How do you calculate the heat absorbed, right? So the work is what? nRT ln. In the first case, A to B is isothermally expansion. That is a PV equals constant, right? So nRT, the work done is nRT ln V2 by V1, right? So that you have P naught V naught by 2. Right? Then in the second step, you have B to A. What happens? Constant pressure. So P times dV, right? P dV, right? P is P naught by 2 times V naught minus 2V2, 2V naught, right? So you have a work done. Then finally, the third case, it is heated, right? It is heated at constant volume. Constant volume, there is no work done. So constant volume, there is no work done. PdV, dV stays constant, right? So C2A, there is no work done. So this is the net work. So we are calculating not the heat done here, heat absorbed here, but the work done. Okay. So now, if you want to calculate the heat absorbed by the ideal gas, right? Which steps will have it is isothermally expanded means what is the heat absorbed, right? Ms delta theta. There is no heat absorbed, right? A to B, there is no heat, right? Ms delta theta, just heat it up, right? Isothermally expanded means nothing, right? It is then compressed at constant pressure to have the original volume, right? Compressed at constant pressure to have the original volume, ms delta theta, right? So constant pressure means what? So you have T2 minus T1. So that is your delta theta. So ms delta theta. And finally, the gas is heated at constant volume. So again, ms delta theta. So here, ms delta theta, right? Between this and this, and ms delta theta, right? But then, because what happens to the gas? It goes a whole circle. So it re-reaches the same temperature. Okay, so there is no ms delta theta for it. So there is no real work done when no real heat absorbed by it. Okay, so an ideal gas heat engine operates in a Carnot cycle between 227 and 127 degrees centigrade. It absorbs times 10 to the power of 4 joule at high temperature. The amount of heat converted into work. Okay, so this is a tricky question. Okay, ideal gas heat engine operates, so you have the 4 points, right? So you have TDS, right? So the heat amount of heat that is used in the Q1 is what, right? So the efficiency is what? Efficiency is 1 minus T2 by T1 ln V3 by V4 divided by ln V2 by V1, right? So the efficiency is 1 minus T2 by T1. Okay, so this ratio becomes 1. Okay, so because this ratio becomes 1 minus T2 by T1. See, look at this. V2 by this one is equal to this one, right? So these two are equal. Okay, so it becomes 1 minus T2 by T1. Okay, T2 by T1 is what? 1 minus 400 by 500. So you have to look at T2 and T1 in Kelvin. So the efficiency is zero point 0.2, right? So the work done, the amount of heat which is converted to work is, heat is what? 6 into 10 to the power of 4. The work is therefore zero point 0.2 times that. 0.2 times 6 into 10 to the power of 4. So it's really a question of understanding how to calculate the efficiency of the Carnot cycle. Okay, so when you have a Carnot cycle, 1 minus T2 by T1 gives you the efficiency. Okay, so the two adiabatic paths, they have this PA v to the power of gamma equals constant. Okay, and then you take the ratio of the two, right? Because you take the ratio of the two, this factor becomes 1. Yeah? Ideal gas situation. Okay, so finally, the in when we look at this slide is continuation of the proof for the Carnot engine. Okay, so here you have, like, let's say you were able to, okay, so let's say you had work done here. You had a situation where you were able to uh, you know um, create another engine, right? Which so you have consider a Carnot engine C, which is operated as refrigerator, and an irreversible engine. Both are being operated between a hot reservoir and a cold reservoir. Now the irreversible engine, right, has produces work. Assume W1 is greater than W, right? So the Carnot engine is the most efficient you can be. That's what he's saying. In a closed loop. So there is no change in the hot reservoir. Okay. So now the heat absorbed from the cold reservoir is Q1 minus W minus Q1 minus W naught is W1 minus W naught. So the net work done, W1 is a minus W. That ensures that the engine thus violates second law. So the Carnot engine is the most efficient engine that is possible. Okay, so so is it possible for W1 or W prime to be greater than W? No. Okay, the because that would then violate the second law of thermodynamics. So the Carnot engine is the most efficient you can be. If you try to beat it, you will violate the second, because no engine can be more efficient than the Carnot engine. So that is the proof of Carnot's theorem. So Carnot's theorem is basically, given two heat reservoirs, a Carnot engine will have the most efficiency. The efficiency of all reversible engines working between two reservoirs, T1 and T2, right, is the same. So, and the most you can do is the Carnot engine and nothing better than that. So, 1 minus T2 by T1 is the best you can do. That is the ideal engine. Like here, ideal gas heat engine, right? An ideal engine operates in the Carnot cycle means 1 minus T2 by T1. That's the best you can do. Otherwise, this will also factor in and this will further decrease the efficiency. The efficiency will only be less than 1 minus T2 by T1. 1 minus T2 by T1 is the highest efficiency you can achieve with a Carnot engine. I was actually planning to do a little bit also of kinetic theory of gases. But see, we've reached the end of the hour. I will do one more class before I switch to back to restart the system. So bear with me. So students, please understand heat well. We'll do kinetic theory of gas one last chapter next time. But understand heat well, because you, particularly if you are a NEET student, heat has thermodynamics has two questions. Okay. If you are a JE student, particularly you're planning to study mechanical engineering or some other metallurgy, etc., right? This is a chemical engineering, very very important science, thermodynamics. But also you will need to get all the marks that you can if you're going to be taking the JE mains, or and if you're taking like good set or you're taking UP set. All the students that who are working with us, who are taking good set, UP set, please study thermodynamics very well. Okay, we are looking to all of you to do well. We are proud of you, just as your parents are, and we want to see you succeed. All right, thank you very much.